Let us start the lecture for the part B of the course linear systems and control. So the part B of this course mainly contains two components. The first one is frequency response analysis. And then the second component is state space design of control systems. All right. So these are the schedules from week 8 to week 12, right? Those are just very brief or rough schedules, right? Depends on the difficulty of each topic. We might have to use 1 hour, 2 hours, or whatever, right, to cover the topics. And then the tutorial starts from week 9 to week 13. Right. So usually the topic covered in a week, for example, the week 8, right? We'll run the tutorial the week following that. And there's an assignment for this part 2, right? You have to submit it online to Moodle on week 12, I think, right? And as usual, right, the Tuesday we'll have a 2 hours meeting in the afternoon, and then largely that will be the lecturing. And then on Friday, the first hour will be the lecturing, and then the second hour will be interactive tutorial. And I want to do a little bit different in the interactive tutorial, right? If you have questions that you want to raise during the interactive tutorial, right, I would suggest you to write it down on a piece of paper and then put it here during the break, right? And we'll try to go through the answer to the whole class instead of individually 2 or 3 of you, right? Agree? Any other suggestions? Okay, good. So this part of the course, part B, we start the first component on frequency response methods, right? And one question: if you all got the lecture notes from Moodle, do you? Is that okay? Yes. Right. And then for part B, right? I am not preparing to read through the lecture notes, right? You are suggested to go through the lecture notes before you come to lecture, and then I'm not going to read through it as it is. On the other hand, I'll run some computer-based simulations and then some workout examples. So first of all, let us. First of all, what is frequency response analysis? Okay, we will try to run an example. No, not this one, the other one. Okay, in this example, we try to simulate a mass damper spring system, and then it should be what we will see. So we wait for a while. The computer is busy. Oh, so long. Okay. Okay, what we see here in this simulation, it is suppose a vehicle suspension system, right? Sometimes we'll go through the road surface, right? It's kind of a sinusoidal surface, and this surface contains different frequencies. And then the response of the mass thermostat system is a function of the frequency. For different frequencies, you feel that your vehicle is moving at a high amplitude or in a lower amplitude. So what is the detail about this mass spring damper or suspension system? Let's just take a look. Okay, suppose we have a vehicle. And it is moving, sometimes could be on a flat surface, and sometimes over the ramps, like this. In one of the wheels, we have a suspension system, and we can model it in this way. So we have the mass, M. In this mass, we define the direction of movement, the x, upward. So, and for a suspension system, we have a spring constant K, and then we have a damper coefficient B. And then we have the reel, and then it goes through the surface. So if the peak of the surface, the distance is L, and then this vehicle is traveling at the speed V, and then it corresponds to a period of time that your vehicle will go through one cycle of the ramp. And then if this T is different, here we have different T. Then it means that we have different input frequency. Different input frequency to the system. Okay. And then we define the input also in the same direction as the U input. So for this system, how it responds to different input frequencies. First of all, we have to build a model. We start to build the model from the balance of forces. So we have the mass of the vehicle. It accelerates. So we have m as times acceleration, that is the twice differentiation of the movement against time. And then the spring and the damper will generate the restoring or the reaction forces. Right? So it is for the damper, it's proportional to the time derivative, and then for the spring, proportional to the distance. Okay, I agree with this modeling. Any question? Then we continue to work it out. So we have minus bx dot plus bu dot minus kx plus ku. Okay. And then we transfer all the x to the left hand side. So we have mx dot plus bx dot plus kx equals ku. Then it involves a differential equation, right, with twice differential against time and once differential against time. So the easier way to solve the differential equation is to take the Laplace transform. So if we take the Laplace transform, then we have the m s square x plus sb x plus k x equals sb of u plus k and u. So in taking the Laplace transform, the twice differentiation becomes the square term of the s variable. And then we factorize out all the x and all the u. So we have the m square plus bs plus k. So it equals bs plus k and then u. And then we looked at the u is the input, right? And then the x is our output of interest. So we have the u as input and then x as the output. Then the transfer function is the output divided by the input, right? So we have the output here, the input here, and then we just exchange the multiplication in the bracket term into the denominator. So we have the ms square plus bs plus k, and then bs plus k. So this is our transfer equation. So the transfer equation, it relates the input to the output, and it depends on the system parameters. And in this case, our system parameters is the m, b, and k. Then what we see with the frequency response, frequency response, it is given by putting s equals j omega, which is the definition of the s variable in Laplace transform. And then we rename the transfer function as G as of defined with the J omega. So we have the J omega B plus K, and then it's minus M omega square plus K plus J omega B. So the important thing here is that J equals square root of minus 1. It is a complex number. So in order to find out more characteristics of the system in terms of the frequency response, right, we need to look at functions of complex numbers. Okay, yes? I'll try. So is it okay or not? Yeah. So it's better? So for the complex analysis of a control system, we need to look into a mathematical tool about complex numbers. Okay, are we ready to start looking at the complex numbers? Okay, then we start looking at the complex numbers. So we say that a complex number in fact it is from the lecture notes, this lecture notes, right? So if you hook up to if you hook up to Moodle online, then you can see this, or you see these lecture notes. The complex number, okay, arises because we need to seek solution of x squared equals minus 1. So minus 1 is a negative number. So the solution is x equals minus 1 square root. So this is defined as a complex number. And then we use the notation. We can use I or we can use J. And then in most cases, J is the preferred notation. And it is also what we're going to use here. And then the complex number also means a ordered pair. Okay, also refers to an ordered pair. Another notation, right? Is a pair. So this one is a pair of numbers. And then we also define the real part and the imaginary part. So in complex number contains two parts, the real part and the imaginary part. Okay, so far, okay with this, the definitions, the notations that we use. Then we look at the arithmetic operations. So the first one is addition and subtraction. So if we have a number Z1 equals x1 plus jy1, and then Z2 equals x2 plus jy2, and then we add them together. How we add them together is this: the real part plus the real part 1 plus the real part 2. And then it is the notation, the complex notation. It is imaginary part y1, imaginary part 1 plus imaginary part 2. So the result is z equals z1 plus z2. So it is x1 plus x2, the real part, and then the imaginary part. So this is the real part, and then this is the imaginary part. And then for subtraction, so we just invert the polarity. Invert the addition to subtraction. This one. And then, however, this one is not changed. It is only within this addition operation we change it to subtraction, and then also this addition we change to subtraction. Okay. So our next set of operation is the multiplication and then division. So if we look at the multiplication, so again we have z1 equals x1 plus jy1, then z2 equals x2 plus jy2. So the multiplication is a cross-term operation. So we have x1, x2, and then x1, y2, and then y1, x2, and then y1, y2. So we have the wanted result. So we have the x1 times x2, and then plus j x1 y2, and then plus j x2 y1, and then plus j square y1 y2. And then if we recall the definition, j equals minus 1, and then j, so it implies j squared equals minus 1. Right, then we have the multiplication equals x1 or x2 minus y1 y2 plus j, and then we correct the term j here, so x1 y2 plus x2 y1. So we have the first two components. So these two are the real part, and this is the imaginary part. Is that okay? Any question on this? If no, then we continue to look at the division. So again, the same as before. And then if you want a result, this Z1 divided by Z2. So it means that we have x plus x1 jy1, and then x2 plus jy2. Here we use a small trick here. Right. We observe that what we can see is that if x2 plus jy2, if we multiply by itself but change the polarity of the imaginary part, so we have the x2 square plus y2 square. This 1 is a real number itself. So it helps us to do the division, right? If we have the denominator as a real number. Then, of course, if we multiply the denominator with the complex number x2 minus jy2, then in the numerator, we must multiply with the same factor. So we have the result is and then for the numerator part, okay, we can recall the procedure in multiplication. So that our result becomes the x1 x2 plus y1 y2, and then plus j x2 y1, and then all divided by the real number. So we have went through the basic operations, the addition, subtraction, multiplication, and division, right? And we will heavily use those procedures in calculating the frequency response of a control system. Okay, any question so far? Then we will look at further definitions, right? We call a complex plane. So if we have two axes, the real axis, and then the imaginary axis. So any number can be projected to a real part somewhere here, and then it can be projected to an imaginary part. So if we have the x here, if y here, then our complex number is x plus jy. So if this is a graphical representation in the complex plane, so it's graphical illustration. So and then we also define another term called the conjugate. So it is the inversion of the polarity of the complex component. So if we have the Z1 equals x1 plus jy1, then the conjugate is so we have a symbol, right? X1 minus jy1. So this is star is a symbol. And then it is the inverted plurality. From the complex plane, we have further representations of a complex number. So we have again the two axes, the real axis and the imaginary axis. If we have a point somewhere, we can also define the point using an angle, and then there's a magnitude. So it is the magnitude. We just call it R. Okay. So this, we call it the phase angle. So because the axis here is a right angle axis, so this is also a right angle. So the magnitude, so R equals the x squared plus y squared square root. And then the angle is the arctangent, okay, is y over x. From the polar form representation, so this is called the polar form. Polar form representation of a complex number. Okay, so far, any questions so far? Then we look at two operations in the polar form. Okay. So if we have the z1 equals x1 plus j y1, so it is also equivalent to the magnitude 1, and then cosine theta 1 plus j sine theta 1. Okay, because of the right angle triangle definition. So if it is r and then there is theta, this part is the cosine theta, this part is the sine theta. And then if we have the Z2 equals x2 plus jy2, it is equivalent to the magnitude of 2, and then some angle theta 2, and then the sine theta 2. Then our required product Z1 times Z2, so it is R1 times R2, and then the product of cosine theta 1 plus J sine theta 1 multiply with cosine theta 2 plus J sine theta 2. So we'll see here is that the multiplication in the polar form so it is the multiplication of magnitudes. So what about the angles? So for the angles, so we have it is equal to the magnitude, and then for the phase angle, it is the sum of angles. So the difference is that for the magnitude, it is the multiplication, and then for the angle, it's the sum of the angles. So why is that? Why the multiplication could become the addition of the angles? Any idea? How do we arrive at this summation of the angles in place of the multiplication of angles? Then we can arrive at the summations. Okay, let us take a look at some geometry. So if we have a point P here, and then if we have another point Q, another point. So each point P or Q can be represented as a complex number in the polar form. So for example, for the Q here, it has an angle alpha. And then there's another angle that is beta. So pay attention that the angle beta is not with respect to the x-axis. It is the difference between the point P and Q, right? Here, the difference is here. Then we draw the projections. And then we call this point R. And then another line that joining the points P and Q. So for this triangle, then we have this also the alpha. Right, but this is 90 degrees, this is 90 degrees, and then we have this the same. Then a little bit complication here. This point is the origin point O. Okay, and then we call this point point A, this the point B. So we have the angle, the OQA. This O, Q and A. Okay, the OQ and A here it is 90 degrees minus alpha, this angle. So it is pi t minus alpha. And then the angle, the RQO, it is alpha. Oh no, this one. RQO, this one is alpha. QP. Okay, so this is also alpha 100 degree 90 degree minus alpha, and then RQO. Okay, so RQO here it is alpha here, RQO. So we have angle RQ. RQP, yeah, it is also equals 90 degree minus alpha, and then another angle, the angle RPQ, it is also RPQ, it is also alpha. So if we let the OP, this point, equals 1, right? For other values, it is just a scaling factor. Okay, then we have the PQ equals sine beta. PQ is sine beta. And then the OQ equals cosine beta. So now we also consider AQ equals OQ sine alpha. So this is this part AQ, right? With respect to the alpha angle here, so it is sine here. And then with OQ equals cosine beta. Okay, so it is cosine beta sine alpha from the OQ here. Then we also have the PR equals P and then Q. P cosine alpha. So now we are considering the right angle triangle PQR. Right. from the PQ, we have the cosine here. It's the same for the 90 degrees difference. So it is equal to sine beta cosine alpha. The PQ here is defined here as sine beta. Also, we see that sine alpha plus beta, the total angle here. Okay, so it is PB. We are considering this right angle triangle, the OP and B. So it is PB over OP. So P and B equals PR plus BR. Right? And then we defined OP equals 1. So it is divided by 1. Right? And then it is also equal to PR plus AQ. BR, the length of B and R is equal to the length from A to Q. So the important thing is here, we see that it is the total angle. The total angle alpha plus beta. So we have the PR plus AQ. And then what is PR plus AQ? PR is this part. Okay. And then AQ, it is this part. So we come up with this result, and then we refer to the multiplication of the complex number. Then we also, if we just put the alpha and alpha 2 as different notations, alpha and beta, then we have the summation of the angles with the multiplication. Okay, is that okay? Then to the division in the polar form. So again, if it is 1 equals R1, right, cosine theta 1 plus J sine theta 1. And then Z2 equals R2 cosine theta 2 plus J sine theta 2. So the division equals is 1, 2. So it is R1, R2. And then the result that we can see here is that it equals cosine theta 1 minus theta 2 plus J sine theta 1 minus theta 2. So we observe that division of the complex number it is the division of magnitude. And then the angle becomes subtraction of angle in numerator by angle in denominator. So these are the important operations of complex number. Right? We can do it in the Cartesian coordinate in the x and y. We can also do it in the polar coordinate. And then in the polar coordinate, it is extremely more simple. Right? If we do it in the polar form for the multiplication and division. Okay, in the last part of the lecture here now, there are some exercises, and then we will go through it in the tutorial next week with our tutors. Okay, so okay, then we will take a break here, and then we continue with the interactive tutorial.
registration times this afternoon at 4:30. So we're just wondering, is there any way we could get the papers now? Like, just look through the papers now?
I would like to stay here in case students still have questions.
Okay.
It's my last Friday here.
Yeah, okay.
But after 12, it should be between 12 and 1, because at 1 I have another thing.
Okay, perfect. So 12 and 1 you'll be
In my
office? Perfect. Okay, we'll come get our papers then. We'll just look through them. Thank you.
Hi.
So firstly, you got a screenshot of that one.
And for this, I need to, if it doesn't come up, I need to contact someone who's there. Like,
Which one? You mean that one?
yeah, because I've already completed the process.
Yes. The other one is this one.
Yeah.
You take the screenshot of this one. Oh, why? I remember I've already got 100.
You must have done that. All you
Submitted. No. Why there is no marks?
Which page did you go? This page? Yes.
Yes. I think I've already done it.
You
Anyway, I've already screenshot.
They have finished mark over there, right? So it's done. It is written finished.
I've already finished.
It's written.
Finished.
Yeah, so you can just take a screenshot.
I've already screenshotted the marks.
But for the other ones, like the
You mean?
other ones which you have over here, yeah, works.
Yeah. I did it, but I do it again.
You have to do it here, right? You have to finish.
Yeah, I've already finished. Anyway, I think go back to tapering the.
So is your annual review done?
No, I don't have. I only just started this week, so I don't have one until November. I think.
Yeah, it's after the end of the second semester. Usually you have.
To get some sort of progress happening. I'm doing some stuff in the wind tunnel, and we went to go and use it 2 weeks ago, and it's broken. And like it worked all last year, and now this year it's just broken. Nobody knows why. So we've got to get this other, like, we had a company that came to but they didn't turn up. So they rescheduled for both. It's taking forever.
Yeah.
Like I had all these experiments planned, and now I can't do them. I'm just running some simulators.
Using which software?
Just actually CSV. It's nothing like super fancy, but just to get some basic data. Like, yeah, mostly like pressure and flow, not something so
So use Fred and the Fred.
don't get what Ronan got. Yeah, here. That was his spot for this one. The center I got two. No. So this one is this one. And yeah, like I got all this. That's fine. Cool. But when I got this solution, I got real. I got very unstable pulse. Oh, okay. And when you plug in the RV, this,
So if the stop sign comes from there and then what?
like, wait, things go that way. But yeah, they definitely start. Like you can clearly see that that's stable.
Yeah.
I'm getting really positive. So I'll show you.
No, sure.
Just wanted to put that. Yo, what's up?
Guys, can I ask you both? One of the demonstrators for the crew will not be available in week 13. Is it you or? Someone asked me and I found the replacement and I forgot who the original one. So it's not you who asked me. Anyway, Yang is replacing that person. She's asking me now, whom am I replacing? And I said, I don't remember. I know there was someone who wanted. Anyway, I'll keep asking. It's my last Friday here. I assume there are questions on both ways. Someone told me it could be Kasha. I'm waiting for him.
I think it's Pasha.
Yeah.
He's going back to India. I think.
I asked Jan to replace him. He's asking whom am I replacing? I forgot. So I keep going around asking people who is. I don't know. I think. often go forward. Or that means you either bring the root well, or maybe not just some rounding up or whatever truncations. So as a result, just yes, it's very close. Yeah, yes, the initial point. In fact, the only explanation one of you will doing some rounding up, rounding down, truncation, whatever. So I think occasionally they ask me about good looks or past tests or whatever.
When's their assignment due?
17th of May, so 3 weeks from now.
That's assignment A.
Yeah, that's Monday. I thought since half of them had a lab on Monday and the assignment is already there, they will have some questions.
Yeah.
But next Friday when I don't come, they will have a lot
Yeah,
of questions.
And it'll be about everything. It'll be about all the
Yeah, and these things.
coding stuff and the lab and the assignment.
So as I said, Linda, if you get questions on the assignment, feel free to send them to me because I'm simply not briefing you at all. You have enough things to do with this. So just if you don't know the answer, that's okay. Just tell them to ask me, and I will handle those. I'm happy to do that. Yeah. Sorry. Yes. Yes. Well, yeah, you will have the formula for the breakaway points, for asymptote for the centroid and for the angles of the asymptote, and also the arch angles. What else? So all equations for distance. No one expects you to give up. No, you won't get rules 1, 2, 3. You need to that. But for example, you will be given you will be given this equation, but you need to know how to apply. What is the relevance for sigma and for phi. You also for breakaway points, you need to know how to apply this. Departure points. I'm not saying this is the formula for couple departure points. I just give you the formula. So you need to recognize that the formula you need, and you need to know what to do with it. But not memorizing, not deriving, not cheating. I know. You can have a look at it. You can have a look at it. You can complain about Mark. You can discuss it in general with me. You can take a photograph of it. That's all fine, but I have to keep it. My consultation times. Today is 4:30 to 5:30, and Wednesday is 5:30 to 6:30. So Friday, 4:30 to 5:30. You have to be at that time. If not Wednesday, 5:30 to 6:30. If it's still not good, then send me an email or a separate time.
Didn't the dynamic students have their test yesterday?
Yes.
How'd it go?
Well, I still don't know.
Well, they seem
I
fine.
think almost everyone turned up.
Okay.
That's all I know so
That's
far.
good.
Yeah, one didn't, but he told he had a clash and proved,
Oh, okay.
proved that. So I believe everyone's there. I didn't count heads, but how filled the room was. No major complaints. I made
Same format?
Same for five questions, 12 marks. Was it the same last? 5 questions and 2 was good. Some questions, 3 questions.
Yeah.
I made a typo actually once, you noticed early enough, fortunately, that instead of CM alpha, I wrote CL alpha. I was probably thinking ahead of the next question.
Oh, okay.
So I don't know why I would type CL, since I was copying from my notes.
Yeah.
And I still managed to make a typo, so I made that correction. And apart from that, there were no complaints, no issues.
Oh, good.
Until they get mine.
That's right.
They were like, oh, you made a typo and I lost 5 minutes
No.
because of that.
They'll always complain.
Some always.
And they have the labs next week?
In 2 weeks.
Oh, okay. Oh, maybe.
But they're still setting, I mean, again, they're going back to the old.
Yeah, I know. I saw OMS setting it up.
Yeah, because the new wind tunnel is still sitting there.
Yes, I see it every day. I walk, when I park my car, and every day I walk past it, I see the nice long.
Yeah. Or what I do when I do flight simulation, if I have 5 minutes, I can come up with it. Now I know it's not, since we decided we'll use the old wind tunnel,
Well, we'd
I
like
kind
to,
of don't care. Not that I don't care, I less care,
Yeah.
care less.
well, we were thinking about using it maybe for aerodynamics.
Yeah. I mean, that was the idea. I mean, otherwise it's too expensive
Oh,
for
yeah,
only
for
one
one course, yeah.
course and one lab.
Yeah.
Or one lab course. If we can use it for that, if we can even use it for design.
Yeah, well, we'll
depending
see
how it is
how
going to
we
look like.
change it.
Yeah. So then it was worthwhile buying it.
Yeah.
But if it was only for 6 hours or
no,
a
we'll
year,
definitely
then
be able
it's
to use it.
ridiculous. Yeah. But using aerodynamics, so you will be involved in aerodynamics.
Yeah, I tutored the course last year.
Oh, okay.
we were
That's
thinking,
issue
we
with
had some
Conrad.
ideas.
Yeah, very good.
Maybe like starting with wing design. Just
Okay.
set them as tasks to
Oh,
head
okay.
up a.
I have a thesis student who part of his thesis was to set up the new tunnel, and but because it's not happening, he will obviously participate in setting up the old tunnel. But you can use him,
Okay.
and he doesn't even have to be a registered, demonstrator.
Yeah.
Just because he's doing a thesis, you should do some useful work.
Okay.
So you can rely on him.
Yeah, when we are setting it up.
Yeah. So let me know.
Because did he just start thesis A now?
His thesis now.
Okay.
Yeah, so he will be around next
Yeah,
if he passes this. He'll be around next semester.
See, because I don't know when the OpenJet has to go.
Yeah, yeah.
And that's going to take a while. And then we've got to install the new fan and muffler for the anechoic chamber. And then I'm sure at the same time they might as well put yours.
Even that, I mean, we can rename his thesis into setting up, aerodynamic lab facilities, not necessarily the tunnel.
Oh yeah.
In which case he might be involved into a number of other things.
So even if you could set up his whole system for
He's
the.
not necessarily, analytically very strong.
Okay.
So I don't know how good he is hands-on. If he is, that's a good solution for him to get a good thesis, and also for you guys and me as well to get some.
Yeah, yeah. Well, even even if he's learning, because it's gonna. We as demonstrators don't want to. I guess obviously we need to know how to use the equipment, but if somebody could teach us how to use it, it would make our life. I'll speak to Con about it.
He's going, I believe, through the induction, or he's going with the lead.
Yeah.
And so he will be okay with health and safety.
You know his name?
Nelson Wong.
Oh yeah, I know Nelson. He was in design. Yeah.
Okay. So he's around. I'm a bit worried, that he's not doing anything with this wind tunnel.
Yeah.
And I'm trying to force, do some reading, do some research. I'm not sure how much he's doing. So
I guess you'll find out in a few weeks.
it's too late. Yeah. If he can get some useful work for him,
Yeah,
it
well,
benefits everyone.
I'll probably have a chat because I'm sure Con has to finish the course outline.
It's next
I think it'd be a good idea.
This week is for the stars.
Or if not, even in the worst case, I don't want him to fail. Like he fails this, maybe we can propose a new similar topic starting next semester. So it covers your aerodynamics and my flight dynamics next.
And he could learn it while we're setting up and then apply it the next semester when you're teaching dynamics.
I really don't want. I mean, that's not the idea.
No, you don't want to fail
I
somebody
want to
just.
save him if possible.
We submit to
If he has
He has to help.
save him.
Exactly.
I will save him.
He can't.
Like he has to do some work.
Oh, it's been 1 month or 2.
There's one which is for me at the moment. I'm just trying to set up some
I have to wait for the result to come back.
I saw it once, and that was it.
What's it then?
I don't know, maybe. But like I managed to set up 10 times as much work as him in a day, and he's done it, 6 weeks. You think maybe he's working passing? I don't know.
I mean, only once in my 20 years career here, only once there was a student, this student, who was not coming to meetings at all, maybe first week and then he came in the week 12, week 11.
After you graduate,
And I
you
saw
can
him
work
at school, okay, what do you want now? You think you can pass now, it's
Yeah.
only a few hours until 11 or And then he pulled out a lot of work.
Oh, really?
And most of that was quite good work. So he was the kind of person
Very
who
self-motivated.
he is sitting at home and doing like good work. Apart from him,
Everyone else.
someone is not coming, they're
It
not
really
there.
shows.
Yeah.
There were, maybe last year with Tom's team, there were 11 of us. It was a lot, but there were only 4 or 5 regulars. And of course, the 4 or 5 regulars got good marks. And then the ones that didn't turn up, it's not to say...
There is a correlation, but
Exactly.
it's not 100%.
No, exactly.
So, from,
It's a very strong
then on,
correlation. But there are
I was actually almost very rude. He's coming, oh, what are you doing here?
Yeah.
Did you say Tuesday 2 o'clock? Yeah, we did for the last 10
And then
weeks.
sure enough,
So I was at the verge of saying, look, you're wasting my time. And then he pulled out, a lot of calculations or whatever he did analysis.
Still okay.
Good. No, that's good history. So, so you actually so you shouldn't be biased. That's
That's
fine.
true. Maybe we'll look at in week 13 when he hands it in. I'll have a look.
But with a full-time job in uni, you can certainly not do it.
You said you were away in week 13. Is that to go back to India
Yeah.
before the child born, or
Yeah, the baby is due 30th of May. I'll be traveling on 27th of May.
Okay.
But you never know. It might come before, a couple of 1 week or so.
is she already over there? No?
Yeah, she's over there.
Okay.
So, yeah.
Is she planning to come back after
After a
maybe
few months, 3-4 months,
Oh.
maybe.
It'd be good to be around. I'm guessing it's like with family.
Yeah.
Outside the university. But you, okay, so you're free on Monday. When are you finishing? But it's okay, you have to be a little bit more ambitious and you have extra space. I think these guys are coming in. Okay. That's it.
Sorry, I think we're trying. I know we don't have an awful lot. Yeah, we have finished. Got some here.